Okay, this is if you will, a talk in two parts. This is the first part today, and we're going to look basically at the same problem from two very different points of view. This is the easier part, if you will, or the easier part to grasp, and tomorrow we'll see the stranger part. But keep in mind, we are going to look at some of these issues tomorrow from a very different point of view, but keep in mind they are the same problem, even though they look very different. But today we're going to talk about things that change and what to do to write programs that change or that are meant to be changed easily. So for that, we're going to talk about this thing. So why a contest, right? Because the material that we're going to look at in this talk started in 2006 when there was a coding contest for a conference that I was going to attend, Smalltalk Solutions 2006. And the coding contest basically was a matter of, you know, you're given some instructions and an HTTP server, and you're supposed to write a program that plays a game. And if you pass that, then great, and then you go to the finals, and in the finals, then the key aspect here is they will change the program on you. And then you have a time limit, and you have to be able to cope. And I'd like to talk about what happened as a result. So Friday at 9 a.m., we're playing this. Have to write a program that plays these games. The typical game of Pong, but for varieties with their own little idiosyncrasies. So there's the regular Pong, just like everyone knows, you know, two sides. Keep answering the ball. If you don't answer the ball, you lose. Football Pong, in which each side controls two bats, and they are locked with each other. So if you move one up, the other one moves up and down, etc. And so you can use like your offensive bat there to immediately answer something that the other bat can't answer, all that kind of stuff. You could also play hockey, which again you use two bats, but you can move them independently of each other, so you can move one up, the other one down, etc. But interestingly, either you move one or the other, but not both at the same time. And multi-ball, which is like Pong, but with multiple balls. So Friday, 9 a.m. in the morning, I have until midnight on Sunday. What would you do? 63 hours of clock time. What would you do? Just hack it together, right? No. Let's look at this. So basically, I decided, no, they're going to change the program on me. I don't want to write 4 programs that later on I can't change. So if I want to write something that later on I'll be able to change, I need to write more than just 4 little things that just happen to work. So let's take a look at this guy. So how does he play, right? Actually, side comment, right? Actually, I was looking at myself. I play a lot of soccer video games, you know? So I was like, oh, so what do I do when, you know, I play, etc.? So, but anyway, but for Pong, this is easier. So what is he doing, right? So let's see. First of all, there's a division between reality and the guy. The guy doesn't control reality. There's always this, you know, error about whatever you do and how reality reacts. So there's a boundary first. And then there's the actual player. So what does the player do? Well, let's see. He senses reality, right, with his eyes. He's looking at the ball right there. So he gets some idea of, oh, look, colored blob here, white against black background. I'm going to pretend that's a ball, right? Then he says, the ball is moving like this, like that, and my pad is here, there, blah, blah. Great. So let's think, well, okay, well, so if all these things are here, then let's decide to do this like that, which invariably will turn into, let's move the pad somewhere and do something, or let's walk first, and, or whatever. You've seen all YouTube videos, whatever. So then answer the ball, and then once you get an objective like that, then actually move and then see what happened, right? Because there's always going to be error. Even if you want to make a great shot, sometimes you're going to throw the ball out, hit the net, hit the other player, hit yourself, etc. So in reality, instead of writing any which thing, I decided to do this. I've talked about this before. But as you can see, it's the reification of what I just described. See, you have the world and the boundary, an interface that knows how to sense the world, then you get ASCII, or it would be color blob, or whatever it is in the retinas of your eyes, and then the eyes would interpret this stuff and would make objects out of it that a strategy could work with. Things like, instead of ASCII for the HTTP server, it would be, ball, pad, position, velocity, blah, blah, all that kind of stuff. Out of that, you get goals, which are effectively functions that need to be maximized. But note, the key aspect here is that the strategy does not say move. The strategy says answer like this. The hands then, looking at the information that was just perceived, decide, okay, in order to maximize these goals or maximize these functions, then I need to produce certain actions, which gets sent down to the interface. The interface behaves, and then the cycle begins again. So, in other words, first thing, make a framework. And this worked out really well, because then, worked out really well. Why? Before I get to that. Worked out really well. Why? Because this scheme allowed a certain degree of flexibility, because then if you change the game, you just change the strategy. If you have two paths, then you make another goal. And if you get multiple balls, then, oh, big deal. I get multiple objects over there, but I don't care. You see, so it's kind of flexible solution. So how did this fare, this 63-hour program? Well, this 63-hour program that could play these 4 games played better than programs that the beta testers for the contest organizer wrote over a month. So there. So I found out later, but note. So then, imagine that you go to the finals and you're given this, right? Let's see. So it's multi-ball, 2 paths, but when you move one up, the other one moves down. And you think, well, oh, and it's called different. Now it's called super, right? And you think, well, let's see. Make a class. On the class side, put a string called super, so the thing identifies the game and knows what to play. Push up a method from the multi-ball strategy to the top strategy so that your new subclass for the strategy can play. Make another objective that when you give it to the hands, if you need to move this down, instead of issuing the command to move the second bat down, moves the first one up. Done. And the program won. Okay. But note here that the whole point of introducing these changes was to make your program break. That was the whole point. Let's try to bother the program and see if you can fix it. And if you can't fix it, then you lose. So, that was wonderful. Then in 2007, I decided to organize one myself. And from the experience of this, I noted that very small changes could have a catastrophic effect because of what happened to the other people playing. So I decided, well, okay, now if I want to organize a coding contest myself, I cannot really choose a problem that has an easy solution. Like, for instance, the first problem I thought of was an elevator game in which you have a building and you have to move the elevators to maximize the throughput of people. But Google found that there had been significant research and there were all sorts of papers, algorithms, blah, blah, blah. So in other words, if I make a coding contest about that, basically the contest becomes implement the algorithm any which way and whatever. So it's not fun. So if you are going to choose a problem for a coding contest, there has to be a problem for which the solution, the obvious solution, well, sorry, the perfect solution is not obvious. Because if not, you don't test anything. You just test anyone's ability to Google and write. And the other thing is that it had to be a problem with enough variability such that you can change it later, and you can introduce enough change, not too much, but not too little, so that you can actually test something. And so I didn't have any idea what to do. And the coding contest was due in April, and it was January. And I really wanted to do something but I wasn't brave enough. And I had no idea. And then I decided, well, let's play some games myself and see what comes up. And I started playing this. So this is kind of a memory game, and a mixture of a memory game and Tetris. Basically, you need to swap pairs and remember where they are, but you see that thing over there? It's growing. Each time it gets to here, you get another row, so you better hurry up. And I played and played and played, and then I realized, you know, maybe I should make a memory game for the coding contest. But of course, you know, you think, well, memory game, how difficult can that be? You know, there's a dictionary, add, you know, a point, put blah, and then, well, if I remember the point because it was there, then big deal, who cares? So I decided to complicate things a little bit and play the memory game without playing the memory game. So I came up with this. So in this memory game here, there are no positions. You see no positions. All you see is a stream of tiles coming to you. And you get to play the game by producing assembler for this little machine here. So what does the little machine do? It has a number of registers. On the A and B registers, you can fetch new tiles. So you can ask the computer to use whatever device it's using to get you a new tile that you don't have from before. And so basically, it's the same as flipping a card. And you can do the same thing on the B register. And the computer will manage not to bring up, you know, the same tile twice and all that kind of stuff. If the pairs match, you can invoke the instruction solve, but if you don't have a good pair in A and B, then you get an exception and then it penalizes you. So, because basically you lose everything, the machine resets itself. But of course, who likes to play with two, right? So you have some memory slots over there, and you must use register X as a transfer register from memory to the solving registers. So basically, between you and me, this is a caching game. You need to implement a caching strategy that can cope. That was the whole point. But dressed in the costume of a memory game with no positions. Now, then, well, how do you make this a little bit challenging? Well, you make scenarios in which, you know, you bombard the poor CPU with more tiles than there are memory slots. Or you bombard it with same, very different, same, very different, same, very different, and see how it reacts. Because then, well, how do you measure how good the program is? Well, you assign clock cycles to all those instructions, and then you count the cycles. And of course, you know, instead of just 1, 2, 10, 50 cycles for each instruction, the exception handler costs you 5,000 cycles. So you make a mistake, boom, you pay. So then you do this. Note, again, that the obvious solution, the ideal solution is not obvious. How do you manage? What do you put in the cache, in the memory slots? How? And then, you know, you start thinking also of optimizations, right? Because let's say that you fetch on A one tile, on B one tile is different. You need to fetch more. So what would you do? Well, let's say you put B on memory 1 going through X. So you issue 3 instructions, right? Like move B to X and then move X to M1. And then you can fetch on B again, right? But you could have moved to X, wait, and fetch on B. And remember that X you need to dump onto memory at some point. But now X is busy. But it saves you an instruction, and then your clock cycles go down. So with this already, you can have fun producing better assembler sequences. So how would you change this for the finals? What would you do? What I decided to do, and mind you, right? Again, this is just, this is called parameter of perception. You can imagine how to write this, right? Because, oh well, big deal, I have an HTTP server again, the interface gets ASCII, big deal, whatever, no change. The eyes, well, instead of producing ball, bat, blah, blah, then now you're going to get, register this, that, the other, tiles, big deal. You get to the strategy what is it going to do? Well, if I'm in this state or that, then fetch or move this, that, the other way, solve. But expresses functions to maximize. The hands then get to express those as actions that get translated into commands that get sent down to the interface and down go to the HTTP server again. Big deal, right? This is the same thing again. So then for the finals, let's do this. First, let's introduce more tokens, but not just any tokens. Because when you play a memory game, you don't bother rotating all the tiles so they are the same orientation. You deal with it anyway. Why? Because you know that the umbrella this way is the same as the umbrella that way. But the key here was to bother this part. How do you produce objects when your data is different? And in the case of the reference solution, it was very easy because the tiles, they would just get, let's say that you had umbrella, and you get umbrella rotated right, umbrella rotated left, and umbrella upside down. So what the eyes did was say, well, if you find any rotated left, rotated right, or upside down, just delete it. So the strategy didn't see anything. Great. That's like a one-line change or something. Then there were less registers. But if the eyes produce proper objects for the strategy doesn't even need to hard code how many registers there are. So again, very simple change, potentially. And you'll notice that the registers are in red, because when you play the memory game, you're not always right. So I decided that the memory slots would be forgetful. They would tend to forget. So what would happen would be that you would move something to X and it would appear that it moved correctly, and then when you move X to one of the solving registers, then it wouldn't move right and it would move something else, as if you had just flipped back something that wasn't what you expected. And then if the hands weren't paying attention to what the eyes were telling it, then you get an exception handler because you would have tried to solve a bad pair. So what we're supposed to do? Well, what happens when you play the memory game and you flip up something that you didn't expect? Well, you flip it back, you flip something else because you know it's around there. So the solution was, well, try the move again. And try the move again in this case is, well, move, hey eyes, check, did it move right? Yes, great, if not, move again. Very simple changes. Nothing out of the ordinary. And again, the people that won very quickly, and the people that didn't suffered a lot. In fact, it was kind of interesting because one of the people that were at the contest told me that his program was taking too long because I had made the search space too big. Oh well. Then I organized another coding contest. And this time I did what in the 2007 coding contest I really wanted to do, which was to model how we work. So I ended up modeling this thing, a work environment. And I also modeled the characters with Dilbert and the boss and the integrator. Here's the garagement for the integrator. And various personalities. It was very fun to deal with Dogbert. What a bad, mean person. And in order to do that, well, what do? Well, you compare this to that, right? So you compare some reference work environment, doing some project, and you count how many cycles they take to deal with the problem. And then you run the same thing, but with the smalltalk program, and measure the difference. So in other words, did adding the contestant's program make the project finish quicker or slower? And then you can derive a score. So how to implement this? Because I also had to write it. And it was quite a challenge, but again, I used one of these guys. Only this time, not as a solution, but as an implementation mechanism. Because again, right, these are just players. Except that they don't talk to an HTTP server, they just happen to talk to the actual program itself. Well, but I don't care because I just change the interface and then I have one kind or the other. And you can imagine that, well, let's see what the game is doing, and you get, oh, here's your work units, and this is how you communicate with others, and I send, these are the emails that you have in your inbox, and da-da-da. So you get objects, and from the objects you say, oh, well, this work unit is ready to be integrated, or maybe I could ask to review from someone else, or I need to delete this email, or whatever. You get goals to maximize, the hands produce commands for that, and they go down to the interface, and off you go. The same thing. The same thing. So, playing with this was a lot of fun. A lot of fun. Because all these various personalities, even something as different as the boss, the integrator, or Dilbert from Ratbert, were just a change in the strategy. Just produce different goals. You have one player that decides to assign work, or you have a player that decides to work, or you have a player like Dogbert. I really like Dogbert. That, when he feels slightly irritated, oh yeah, sure, I'll help you with it, and then he throws it away. And then the boss complains to someone else. You're a nice guy. So what did I change for the finals? Well, the clock ran 3 times as fast. Every clock cycle, 3 clock cycles actually happened. And this was designed to trip up any hard codings along the lines of, well, wait 1 cycle and check for email, because everything took 1 turn. So if you make things run 3 times as quickly, then chances are something's going to break, some assumption is not going to work anymore, and some counter somewhere that always said +1 is not going to work very well. And the other thing is that I obscure the names. Instead of playing with Dogbert, Ratbert, etc., you play with Rodriguez, Juarez, Perez. And so you would have to see, well, did someone actually hard code a strategy to deal with Dilbert, Dogbert, Ratbert, etc.? Because if in that case, then it's not going to work very well. And the idea here was that, well, for instance, if you deal with, say, Dogbert, and you ask Dogbert for help, and Dogbert decides to throw out some code, and then the boss is complaining to you, which makes the project take longer, and your stress goes up, etc., because you're getting complaints from your boss, and so on, and your inbox is getting fuller, so there's more stress, right? Then you should learn not to deal with Dogbert. Stop sending stuff that later on your boss complains to you about to the same person. Choose someone else. The other thing that I did was to break the email server. So every so often, the email server would just throw email away. In other words, let's introduce a junk folder that is a little bit too aggressive in marking junk. So for instance, you basically introduce tension, introduce sources of stress, and see what the program does. Now, for something like this is not hard, right? Because the interface is going to see that the clock is going faster, but it doesn't really care. The names, it doesn't really care because the strategy just didn't hard-code any names. And emails that get lost would just get treated as normal stress. So again, very simple changes. It shouldn't have been that much of a problem, right? But, oh, and here's a summary, right? So here's all that changed. Not a whole lot, right? So in Pong, we changed the string. We changed bats that move one way or the other, and we had a combination of behaviors, multiple balls and multiple bats. In here we changed 10 to 6. You had to retry something, and you had additional data with variability you could easily ignore and throw away. And in this one, the clock was faster. You had weird behavior that you could ignore, and you were tasked to avoid hard coding strategies for certain players. So what happened, right? This happens. This happens. Either you win in 15 minutes, or basically you run out of time. Why? Why? Why such different outcomes for such tiny changes? And this is what we're going to talk about. So, well, This is something that gets on my soapbox, or makes me go on my soapbox. But there's these assumptions about how you write code, right? Let's say you're faced with, hey, you need to finish in a certain time. And so you think, oh, right, the quality of a program times its size must be a constant, right? So the smaller the program, the higher the quality. And the same with the effort, right? If the program is bigger, then you put in more effort. So if you want to minimize effort, because you don't have any more time, then you have to make the program smaller. And you make a program smaller by making less classes and less methods. All right? So everybody knows less classes and less methods, more quality, and less effort. Right? In other words, here we have the troll of Smalltalk best programming practices telling you, you ain't gonna need it, less is more, and keep it simple, stupid. I cannot tell you how wrong this is. It's not the right point of view. It really isn't. Why? Because of this. It doesn't work that way. It's not true. So, but let's say that, you know, that I had to write this with the Smalltalk troll, you know, of best programming practices advice. Well, already, right, too many classes and too many small methods. So let's start ditching stuff. Well, first of all, who cares about objectives if you're already doing the actions? Just throw them right from the strategy to the interface. In other words, hard code what the commands are for the HTTP server all the way up into the strategy. And then you have less objects, right? You don't have objectives, you just have actions. You can put them in as a string, just hard code the whole thing, throw it up there. Awesome. Then, well, why bother then with going through ASCII, through objects, through the eyes, etc. Let's have the strategy talk directly to the interface too. And then you get rid of more stuff. Then let's put the eyes to the side, call it a helper, call it a parser, because it's kind of cool. And now you have, you see, less classes, less stuff, must be better. Less classes, less methods, maybe bigger methods, but who cares? I'm in a hurry. So, and you know, oh look, my code has something called parser, haha. You know, it must be great, because I understand pegs or some such. Well, the problem with this approach is that you end up with this. Something that knows way too much, has too many responsibilities, and imagine then having a huge object full of stuff, and then someone changes a little thing. You end up having to make a subclass, copy down methods just to change a few constants here or there. The changes kill you. They just take too much time. In other words, the troll of computer programming best practices is really telling you, don't worry about version 5.0 when version 1.0 is always sufficient. The only, quite frankly, I'm sorry, right? But quite frankly, the only programs that should be written that way should be written in toilet paper. That's the issue. That's the problem. Who cares? If you are going to write and throw it away, maybe you shouldn't be that careful. Maybe the program should be written in the first place. Why? Not for us, right? At least not for us. Because then changes kill you. And certainly you shouldn't take that approach in your production software. It won't fly. Because it will be something else, right? It will be either the multiple bats will turn into, well, the customer says he doesn't like one, he wants many. How many times has that happened? Or it will turn into, oh, shoot, my program is taking too long to run because I have all these singleton things that now become a bottleneck, and I've written everything knowing there was a singleton, and now I cannot introduce many, I cannot multithread my software. Right? That's a problem. That's a huge problem. Particularly when this version was designed to run as multiple processes or one process, and the whole thing changed from multiple processes to one process by changing a single 5-line method. That was the key. That was the key. So, this is the difficult part of computer programming then. And mind you, I chose these slides before Alan's talk, but I know he likes to talk about that. So you have your bricks, right? Your classes, your methods, etc. And you're supposed to come up with a plan, with a way to put these things together such that you can get whatever it is you want, and such that you can change it more or less. That's a key aspect of this. So the key aspect here, right, just as with architecture, is, well, take classes and objects, put them in some way that you can change them, such that you can have something interesting. This is the whole difficult part of programming. And it takes such care, because then you don't really focus anymore on getting something that works any which way. That stops being the focus of the issue. The focus starts being on, well, what is it about this problem? What is it about the pattern of this problem that I can first think about, such that I can distribute responsibilities between different objects, such that I can get something out of the interaction between the objects rather than the objects themselves. Which is the same thing Alan said yesterday about the arc and all that. Stop putting the bricks any which way and use the same bricks, the same rocks, just put them different. Assign them different responsibilities. For instance, in the case of the arc, instead of holding weight only upside down, maybe you need to distribute weight sideways. Sideways first, then down. That's the whole point. But it's so difficult, because this is such easy material to troll. And the danger is, well, if you let your design be trolled to death, then this happens. That's the problem. That's a huge problem. And then you cannot change your software in 15 minutes. It always takes 2 hours, 3 hours, 5 hours, 10 days, 20 days, 30 days. You lose customers that way, because you can't change your software anymore. So, the whole point of this, then, is don't have one idea. Having one idea is not enough. It's not enough. Why isn't it enough? Because if I only thought about one idea, then I would be content enough to start writing code right away. And then I would miss the abstraction. I would miss the relationships between the parts that become evident when you start changing initial conditions a little bit. For example, if I hadn't bothered with the objectives, the difference between the objectives and the actions, remember, then the bat that moved one way versus the other would have meant that somewhere I would have had to change some hard-coded thing into something else. And I would have probably had to make a whole subclass, or even better, just change the code any which way, right? But let's say, make a subclass, copy down the method, change some hard-coded thing, etc. And with objectives, it was just a matter of adding one class with one method. Or the difference between having something that was either multi-bat or multi-ball would have turned into, well, let's copy some methods here and put it in a subclass, and then grab some methods from some other class and copy them over there and mash them any which way, and maybe it works. And in the other design, it was just a push-up. Like refactoring, push-up, done. And if I had hard-coded the string somewhere, well, that's again another class just to put in a new string, etc. It's just limiting. This is the whole point. You cannot have just one idea. Actually, this picture, the picture of the single light bulb for an idea, is wrong. It should be more like this. You have to have a family of ideas. Think about a variety of problems first. And see, well, okay, this one I've solved like this. Okay. Don't code. Stop. Just put it to the side. Stop. So if I change a little bit, well, I would write it like this. Good. No code writing. And this like this, and this like that. And then you see what is common between them and what changed. And if you do this enough, experience will tell you in which places you have to add a place where you can add variability or flexibility to your design. either with Pong, or with the memory game, or with the coding game. Now, how do we express that in Smalltalk then? What is the main mechanism? Well, the main mechanism to deal with this is a change of boundary. You cross a boundary. That's a main mechanism to express flexibility and change of behavior. Because when you send a message, you can potentially send the execution context to some other object. But if you're only in the same class, you cannot change anything, and that's why it gets complicated. Or, if you have methods that are super big, changing something in them forces you to copy the whole thing just to change a little bit, and that's costly, and it's not flexible. Or, if you don't have enough classes, you end up having to copy the whole class just to change something else, where composition and delegation would have been much better. So, when the troll comes again and tells you, oh, you ain't gonna need it, stop creating so many classes, because everybody knows that making a program bigger takes more effort, so you should stop it. No, just think of this and think, well, yes, but if I don't add those pieces, tomorrow things are going to change, and when they change, I won't be able to change my program quickly because it won't be flexible enough. It's like building houses with rocks 10 meters by 10 meters. There's only so many interesting houses that you can, or rooms or bedrooms that you can build with a 10 cubic meter rock. It's a problem. It's too big of a brick. It's the same problem. Or, well, stop adding so many methods, and what's this with double dispatching? Just inline the whole thing and use this kind of. Well, yeah, it sort of works until tomorrow when someone decides that you have new requirements. So, this is the then program family that came out of this single pattern. You have something that knows how to play 5 games of Pong, and you have something that knows how to play 2 varieties of a rather different memory game from one another, and you have a coding game player that can pretend to be Dilbert Radber, Alice, Wally Dogbert, the garbage man, Asuk, the boss, or a smalltalk program, and they all run with the same pattern, with tiny modifications in between, and the same pattern stays the same. And they help you, and the pattern helps you structure a family of solutions that address very different problems, but because you have a pattern, and the pattern is flexible, everything inherits the flexibility, and then you don't have to wait until 2 hours until you run out of time, and you can change your program in 15 minutes. So, I think the talk ran quickly because I was thinking that I would get interrupted, but I didn't. So, do you have any questions? And if not, we can go to the break. Yes?
I have a question. Do you think there's if somebody starts running, having what you say in mind, is there a risk of creating more classes and methods than necessary, like having wrong change of delegations that make it harder to understand and follow the code? Do you think that's a risk? And then, what's worse, to err on the complexity side or on the simplicity side? Or your view?
There's always the risk of going overboard with things, either with flexibility or with rigidity. We see it in various ways, such as, let's go overboard being afraid that something can happen and then you have static typing or whatever. Personally, I think that erring a little bit on the side of flexibility tends to be better. Because if you have flexibility you don't want, then it becomes obvious, because then you end up with classes that basically pass all the messages through and do nothing, or messages that simply say, well, do this, self do that, self do that, self do that, and then something happens. So it's more or less obvious that you have something extra. But usually then, because you have enough classes and you don't have complicated code, it's easier to change, because it's easier to identify, and you end up deleting a few little things here and there, and it's not so shocking to a program. But on the other hand, if you're on the side of less methods, less classes, less flexibility, when you want to change, often you end up having to rewrite the whole thing or engage in a major refactoring exercise. That is very, and in my experience, it tends to be more costly.
So you think that when you start exploring a project, you better err on complexity and start doing more things than start from something simple and then growing into something more complex?
Guided on experience, yes. For instance, I have an example of how to write initialize methods, for instance. Is a typical thing that happens over and over and over again. You write, I don't know, domain class initialize. Well, initialize this, this, that, the other, and usually what happens is you end up doing something like, I don't know, self foo, dictionary new, self bar, sorted collection with parentheses, you know, sort block, blah, blah, this, that, the other. And it works, and you think, oh, yeah, it works. I don't need anything else, keep it simple, stupid, blah, 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 all that. Until you make a subclass, and now the difference is that in foo, you don't want a dictionary, you want an identity dictionary. So because you don't have the flexibility there, you have to copy the whole thing down, and now you can't even send super. Where it would have been, huh? But hold on, when it would have been better to say, well, you know, self foo, colon, self new foo, self bar, colon, self new bar. And then when you need to change something in a subclass, then you simply say, well, new foo is identity dictionary new, and nothing less, nothing more changes. And over time, you end up building some sort, I mean, if you pay attention to these things, over time you end up building some sort of library of very common patterns in which things tend to change, and less than ideal solutions that you take first and later on you pay. So over time, I'd rather err on the side of flexibility. Any other questions? Yes?
My own experience tells me that more code not always results in more flexibility. Actually, most of the time, straight away.
My implication was that having a guideline that says less code must always mean less complexity is not necessarily true. But it shouldn't be taken to imply that, what's that?
More code don't mean more flexibility.
Right, well, my main implication is that if the usual advice is that less code is better. Oh, okay, I see what you mean. Yes, it's true. If you have methods like this, it's not flexible. I think we all see the effects of that in the small talks we use where we visit our least favorite classes. But I don't necessarily agree that that should be grounds to say then that more code should be automatically labeled as a defect or potential problem. I think it depends. Any others?
Yeah, I got one.
Go for it. What time is it?
Yeah, well, it's late, but I'm going to ask anyway.
Yeah, sure.
I think you're making a mistake when you say that the acne keys is not good because you're just looking at that, let's call it rule. And when you're designing, you have to take care, I mean, you have to work with a lot of rules or linguistics at the same time. The idea of that neo keys is not to start writing more code or to start having big methods or those kind of things. You have to keep thinking about coupling and cohesion. So I think that saying that you don't have to do that neo keys or whatever is not saying that it's not a good idea doing that. It's not taking the whole picture how you design. And the other thing that I have to
well, can I answer that one first, and then you ask me the other one? Can I answer that one first, and then...
And then we can also have a coffee.
Well, let me answer first.
I think I disagree with your idea of how the changes that you made affect the design of the people that work or that in the the context. Because first you had a design, so you got the changes based on your design, and you're thinking that the changes that you're making are going to affect in the same way the design that the other people did, not based on how you thought the problem, but based on what data they and on what those people understood about the problem. So I think that your conclusion about they did a wrong design because they couldn't make it work in such amount of time is not the only conclusion that you can come up with. So I would think a little bit more about the implications of that.
With regards to Yagni, Kiss, and less is more, in my experience, I've seen it, and this is perhaps not from, say, a context of education or research. This is more from a point of view of industry. I personally have seen those arguments used way too often. And the result is code that is extremely hard to change. My main gripe with those arguments is that they are used effectively to shut down anything that doesn't conform to someone's limited ideas. That's in my point of view. I've seen it way too often and the results are bad. So what I'm trying to say is, look, no, it doesn't really follow. It's not that simple. With regards to the changes, I did not know, of course, what the programmers would do. I didn't necessarily read their code. I tried to pick changes that, although were not too complicated, they had something in them that in my experience would have resulted in problems. Typical stuff: hard coding of strings, lack of flexibility for refactoring, that kind of stuff. And what I noticed in these three contests is that in general, people can deal with the changes easier when their program has basically two traits. One is a less rigid connection to the particulars of the problem, and another one, the ability to be refactored on demand in short periods of time.
I did the contest in 2000.
I know you had a bad time.
No problem.
Okay, we'll talk later. All right, thank you.